Hello again. Tonight we're going to talk about something that I'm just going to postulate throughout there as a capability that we might be able to develop as the people living on this planet. Solar System Observation Network, right? I just gave it an acronym. Everything's got to have acronyms. Okay, so from our vantage point on Earth, you might think we can see anything in space, but there's some directions that we can't look, and there's sometimes places where we can normally look, but for either short or long periods of time, we can't look because something's in the way. So think of it as if you've got something that's in Earth orbit, like the Hubble Space Telescope, it can only see out into the part of space when it comes around to that side of the Earth because the Earth is in the way. Or if you're at an observatory on Earth and you want to see something out in space, it could be behind the sun, like a comet, or it could be behind the moon, like an asteroid. Actual observing of things when they go behind other things is called occultations. And there are a lot of people that focus on occultations because there's interesting information that can be garnered as you watch something disappear behind something or reappear from behind something. And then there are the larger planets in our solar system, Jupiter, Saturn, Uranus, and Neptune, that when something further away goes behind them, they're going to be behind them for an extended period of time because their orbits are so far out in the solar system that they move slowly across the sky. And then there are things like the James Webb Space Telescope, JWST, that's out at Lagrange point 2, about 1.5 million miles away from Earth. Think of it as if you're on the Earth and you see out towards the moon and then you go out further than the moon, then that's kind of the elliptical orbit, 90 degrees to that point, where JWST is at. It's where Gaia was. And it can't turn back around because if it did, it would be facing towards the moon. And remember, when the moon is new from our perspective, it's full on the opposite side of the moon. That kind of brightness would be damaging to the infrared observing instruments aboard the JWST. Or if it was facing towards Earth, same sort of thing. And even worse, it was facing not the moon, not the Earth, but beyond the Earth, the sun would be there and that would destroy the instrument. So there's some directions that JWST will never be able to look at. And if it wants to see something on that side of the sky, it has to wait until the Earth orbits around the sun, and then JWST can point away from it. What about the instruments themselves? Different instruments have different specific purposes in order to constrain costs and reduce the payload weight for the rockets. Okay, we're going to launch something that only looks using these kinds of instruments and only looks in this portion of the electromagnetic spectrum and looks only in optical or visual light, doesn't look in radio. Or if it is in radio, it's only in these bands. Or if it does radio, it's in these bands, but doesn't transmit, it only receives. So there's no being able to detect surface details or its spinning, its rotation, because you have to transmit the radio, have it reflect off the target, and then you can pick that up like radar. And then we don't have any space-based observation capability currently for gravity waves, for gravitational waves. So whenever we put something out there in order to reduce cost and reduce payload weight for the rockets, we just go, well, this mission is just about this, and therefore is blind in all the other capabilities. So when we put them out there, we can only see things once they come up close. Like we can't see things that are on the far edge of the solar system, except when they're really bright and really large, or they come in a lot closer. And when they're not behind something, we're blind to seeing things that are not emitting, not producing whatever we're looking for in the wavelengths for the instruments that we've created. And until we start sort of removing the blinders, we don't know how much or what is out there until we can observe it. So how do we go about observing it? So I'll just throw this out there. If you want to see more sooner, you got to look for more places. So if you're just observing from the surface of Earth or in orbit around the Earth, things are going to get in the way. There'll be things farther out that you can't see. So I've kind of tossed it out there as the best place to put an observing network would be somewhere between Earth and Mars. You don't want to get between Mars and Jupiter because that's where the asteroid belt is. And you don't want to get closer to the sun because then it makes it more difficult to see dimmer things. And you want to be able to not just stare straight out from the plane of the solar system. You want to be able to look in all directions. If something becomes a target of interest, you want to be able to have one of these observing outposts or stations turn around, look at it. And we need to make them broad spectrum, multiple disciplinary instruments. So it needs to see not just better in optical, but also radio, high energy like X-ray and gamma, as well as find a way to do gravitational wave measurements in space. And this wouldn't be just one satellite. This would be a collection of them. Initially, there would be no crew on board, but I can see these getting to be large enough that they might eventually become things like military outposts. We on Earth, we put military outposts in the most horrible conditions for human beings, but that's the best place for those instruments. Like the dew line up near the Arctic Circle was the best place for us to see when the nukes were coming over the horizon. So we had people that would go there for a period of time, typically because we don't like you, we're going to send you someplace you won't like. So you would get a military outpost in a very uncomfortable location. So these would be the same sort of thing, initially as uncrewed satellites. But I think getting used to calling them outposts would be a good idea. Start by launching just a few of them, just to test out the technical feasibility, and then increase the number of them until we have a complete circular coverage in the orbit between Earth and Mars. And we can look in all directions, not within the solar system, but also outside the solar system and up and down. Maybe we start out by looking in infrared, maybe just mid-infrared, because we have the technology for doing that, and that would make the instrument smaller. But eventually we want more infrared bands, radio, add radar, so we can measure stuff, and eventually gravity waves. See these things coming from a distance. And that's just for the plane of the solar system. Eventually you'd want to have orbits that tilt up so we can actually go above and below the solar system, see more things. So how would these things talk to each other and talk to the Earth? The individual outposts would need to talk to each other so they could relay back to Earth, because when something gets in the way of our communication with that particular outpost, maybe that outpost can talk to this outpost, which can relay back to Earth. And nowadays they use lasers for satellite to satellite communication because you can do it higher bandwidth, greater noise immunity. So outpost to outpost via laser, outpost with Earth. You probably relay from outpost to outpost, and then you relay back to an outpost that is in a position where the deep space network can communicate with the outpost that acts as the relay. And the reason why you do it this way is the deep space network is talking to a lot of things in the outer part of the solar system, as well as now inner part of the solar system. And it only has so much bandwidth, so many channels, so many ears, so many dishes. It can't point everywhere all at once. If the things it wants to see are on that side of the Earth, that means that the deep space network dish on the ground on the opposite side of the Earth isn't being used. Well, you could take one of these relay outposts and have it talk to the DSN dish that's on the other side of the Earth and then relay that back around. So it wouldn't be overloading the DSN. But the idea would be that all outposts would be in constant contact with the Earth in case the AI software on board the outpost said, wait a minute, I was taking a picture over here yesterday. I didn't see that, and now I do. Pay attention. So it could give a heads up for things that are towards the outer part of the solar system. So if you're thinking this is not technologically feasible to create this sort of network and to operate it and maintain it and keep it up to current technological advancements, we already do this stuff. On Earth, we have the deep space network that points out the things out in space and talks with them. If it's on the other side of the Earth, how do you relay that? There's a high altitude Earth orbiting network of satellites called the Near Space Network that actually relays for the deep space network. So when the Madrid station wants to communicate with JPL in California, then Madrid sends up to the Near Space Network. The Near Space Network sends down to the Earth station at the DSN site in California, and then they send it over fiber optic cables to the JPL Operations Center. We do have multispectral weather satellites called GOES, and we maintain those. We'll send up new GOES satellites so that when the prior generation gets old, has a problem, or runs out of fuel, we put that into a parking orbit. We move the replacement in there. So we have the ability to stage these over time. We have lots of geostationary communication satellites, both government as well as commercial ones. Then nowadays they're putting up low Earth orbiting commercial communication satellite networks like Starlink, very popular. But there's also OneWeb, Kuiper. Other nations are putting up their own constellation satellite networks. So, putting up networks of things over time, keeping their technology up to current levels, maintaining them and monitoring them, those are things that we do. So we know how to do this stuff, keep them updated. And when they get towards the end of their lifespan due to solar panel degradation or fuel exhaustion, we know how to deal with that, how to replace them, how to move them to parking orbits, how to burn them up. So we keep it fresh up there. We can do the same thing for a solar system monitoring network. So what would be the benefits of having this thing? If you've ever studied how they know how far away something is, the nearest calculations is via something called parallax. That's essentially if you think of the Earth in orbit around the sun and we look at some distant object, if you're on this side of the ellipse and you look at it, and then you're on this side of the ellipse 6 months later and you look at the same object, it's like blinking your left and right eye to look at a distant target. That angular shift you can use via trigonometry and calculate a triangle and know how far away the base of that triangle to the apex would be, and that's how far the object is. So for things that are relatively close, within maybe 30 light years or so, we can use parallax for that. But we have to wait 6 months, do an observation, wait 6 months, and it's better to do it when the Earth is at the ends of its orbit around the sun, because you can get further out. Well, that's just to the orbit of the Earth around the sun. If you could get out to closer to the Earth, to the orbit of Mars around the sun, you'd have a much wider parallax to get a much better calculation on that triangle to find the distance more accurately. If you have a constellation of satellites that are already orbiting every few hours, you might have another satellite coming into position that might be at its orbital mins or max, and you can do it much faster. If we've got satellites that are deep space probes farther out than this network, we could actually use this network as a relay for the NASA Deep Space Network. It has multiple purposes. And as we're continuing to talk about interstellar objects traversing our solar system, like 3i Atlas or Oumuamua or things like that, we can see them sooner and we can see them when they're farther out. And because the orbits are all the way around the sun, we can see when it goes behind the sun. But because we can see more objects and see them sooner, it's good for Earth defense because we can detect things sooner and see more of them. As well as we can look out farther into the solar system, we can find more moons, more smaller moons orbiting the gas giants of Jupiter and Saturn. We can see Kuiper belt objects. And maybe if the instruments we put out there are good enough, we might start to be able to see objects individually in the Oort cloud at the far edge of the solar system and quantify how many there are actually, because right now we've just got guesses, and determine sort of what the size range of them is through direct observation. Because it's going to cost so much to do this, it's likely going to have to be funded by an international consortium of government agencies. Lots of funding, yes, many, many billions. So it'll be jobs and business for direct and indirect suppliers of technology and products and services. And we'll be advancing technologies that can benefit Earth, like making better weather satellites for better predictions, agricultural observing, all kinds of stuff that we do now with satellites that are in Earth orbit. We can develop even more advanced technology, get them farther out, because if they can do it really great farther out, how much better can they do it when they're closer to the Earth? So we know that all these satellites eventually go bad, run out of fuel, all those kinds of things. What do we do with them when they're that far out and they go away? When you have lots of these satellites out in distant orbit and they start to have problems or run out of fuel, what do you do with them? The satellites that are in geosynchronous orbit around the Earth, there's a thing called a parking orbit where they just shuffle them around. So instead of that geostationary satellite being parked directly above North America, it kind of moves out over the Pacific and hangs there. Now they do drift back towards the US, but it takes, I think, decades for them to become a problem again. But once they do become a problem, not much we can do about it because they're no longer operational. They don't have any fuel left. But once you put things out into a parking orbit, because other things have a gravitational effect on them, their orbital position slips if they don't have the fuel to maintain their position. They could, of course, use the last of their fuel, like the last 25% or something, and instead of staying out at their distant orbit, turn and point themselves upward from the plane of the solar system and put themselves into a high arc orbit that would terminate at the sun. So maybe years later, they would wind up burning up in the sun. Maybe, just a thought. Or as we're developing robotic technology, we could eventually send other probes out there with replacement parts or replacement outposts to, upgrade things, repair things, get them working again. Or it could be a tow truck and get out there, grab something and drag it back in and burn up the tow truck and the defective outpost into the sun. So in summary, you heard it here first, maybe. The Solar System Observation Network, or SSON, of outposts. If you want to see what you're unable to see, look from elsewhere, look from more places. If you want to observe what you can't currently observe, look in different ways. I don't think we need any further advancements in rocket propulsion unless we want to get the satellites, the outposts out there sooner, because we've already proven we can launch a Tesla to orbit around the Sun to Mars orbit. We can put New Horizons all the way out to Pluto. We may need advancements in satellite technology to make their fuel last longer, make their solar panels more durable, that kind of stuff. Given the billions that this will cost, likely an international consortium would be required. Large-scale networks of observing instruments do exist, can be created, sustained, managed, operated. We know how to do all that stuff. Just a thought. But remember, at one point in the, earlier parts of the last century, Earth orbiting satellites were just a thought. Now there's thousands of them up there. And then for those people that want more information on the Hubble Space Telescope, James Webb Space Telescope, the Deep Space Network, the Near Space Network, the geostationary weather satellites, or Starlink, we've got links to those. Comments? Questions?
It reminded me of where they went out in space and got the garbage.
Do you want
the old sci-fi?
Yeah, I think that's going to be a business in the distant future, is getting space garbage. The first place they can start cleaning things up is in our own backyard. There are lots of things that are in Earth orbit that have been around since the 60s and are still in orbit, and you have to watch out for them. So when you want to launch something new, make sure your orbit doesn't intersect at the same time as that other thing. We've got some basically upper stage garbage that is in orbit around the moon. We've got things that were in orbit around the moon that have made it back to elongated orbits around the Earth-Moon system. So yeah, we've got a lot of garbage up there that we need to find a way to do it. There are companies, commercial companies, that are trying to do tugs, like go up there and either push it up to a higher orbit or drag it back down and let it burn up. Problem with that is, given the progression of costs of things, the tug costs almost as much, if not more, than the original satellite, which is, yeah, somebody saw you coming. The tug should not cost as much as the original satellite because it shouldn't have to have as much fuel. For one, it can be smaller. For two, so had anybody ever thought about putting a satellite network out into the orbit beyond Earth, between Earth and Mars? So it's in a circular orbit, just going around the sun, put a number of satellites in that orbital path, do all the observing that you want to do, and just relay it back to Earth.
Sounds like a good idea.
Well, it's always bug me a little bit that people say, well, let's just have the James Webb Space Telescope take a look at that because it's interesting, only to find out it can't look that in that direction. If you wait about 6 months, then it can look in that direction because then it wouldn't have to stare at the sun.
I always thought it would be nice to have an observing telescope, satellite, whatever you call it, in the center of the solar system, but way up high, so it can see all the planets from up there. Right, because we're at the on an edge-looking
Yes,
plane.
yes. We do actually have a probe that was in a tilted orbit. So
Yeah,
it went to go into an orbit around the sun, and its orbit was slightly elongated. So it actually went from beyond Mercury to around the backside of the sun, and they used the navigational thrusters and literally tilted the orbit to almost 90 degrees. So it was going around the top and the bottom of the sun.
great. That's the good idea.
And that was the first time we ever had images of the top side of the north pole of the sun. The problem is they couldn't get high enough to see out far enough to
Yeah,
see planets.
yeah,
It was in a very tight orbit around the sun,
yeah,
but you need to be you need to be up at
yeah.
least, think of the orbital distance from the sun to Mars. Now turn that on its 90 degree side. That's how high above the sun you'd need to be able to see out to the planets. Because if you're too close, you might be able to see Mercury and Venus, but you're not going to see anything beyond there.
But our telescopes are pretty good now for long distance. So if we can get up way up high, look
It
down.
has to be way up there.
Yeah, yeah.
Is there a good scientific justification for doing that other than, oh, it would be cool?
I had a slide that gave you a whole laundry list of the reasons why, the benefits you can get from doing this. The first one that came to mind was better parallax measurements. You can do them more often.
Yeah.
You can do them more often, and you can do them more accurately because they're further apart and further out.
But also, since we're on the edge, of a disk,
Mm-hmm.
anytime we observe anything, we've got to wait for the proper opportunity. But
Yeah.
if we were way up high, looking down,
Yeah.
we could see any planet we wanted to. Just
But you've got to take your baby steps. So first,
Yeah.
let's get the concept of a constellation of these outposts
yeah,
in a farther than Earth, not quite as far as Mars. So 30 plus million mile radius orbit.
yeah,
Get a few of them out there, start showing the benefits of them. And then when it catches on and people go, I think we ought to fund that more. Let's put more of them out there. And then the next step is now that we got a flat disk around the solar system, let's create another disk of these outposts and tilt it 90 degrees.
that's right. Yeah,
Over under. And you're now at a distance about halfway between Earth and Mars, orbiting that way. Now you can see out at a wider angle.
I would see even more than that. You can see Jupiter, Saturn. If you get way up far,
Yeah.
and our telescopes are getting pretty good now.
Yes.
You could look at anything you wanted to.
I mean, the James Webb Space Telescope, because of the heat emissions of the objects, has spotted a new moon of Neptune, one that we didn't know was there. And so they went looking and what's that? Come back and look at it again. Oh, look, it's moving. Track its orbit. Oh, it's in orbit around Neptune. Hey, we found another moon, guys. And they said, no. You have a candidate for another moon. You need to get another observing instrument to peer review, corroborate your observations. Where am I going to get that? So they created this loophole. Well, if you have two different scientific teams do the same observations at different times of the year, then okay, we'll let that be confirmation because we're not building another James Webb Space Telescope anytime soon and putting it somewhere else where it's a different instrument, it's a different position, different time. Okay, we'll loosen the rules a little bit. But typically it requires a lot of differentiation in the observing teams to act as a corroborator or a peer review of an observation of moons around one of the planets. They would even do things like, okay, they were finding moons around Jupiter, but they were using the Galileo probe to do that, and it was in orbit around Jupiter. So it was up close seeing things. And it created a laundry list of candidates of new moons. And it would stay as candidates because we weren't sending probes out to Jupiter. And then when the Cassini mission flew past Jupiter on its way to Saturn, it had the coordinates. So it went confirm, 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 confirm. And now you had confirmed moons of Jupiter. So Jupiter took a jump up in the number of moons. And Cassini went in orbit around Saturn and went moon, 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 found even more new moons than the Galileo probe did around Jupiter, around Saturn. So now Saturn has more moons than Jupiter does, confirmed moons. And they both still have laundry lists of yet to be confirmed. But when you have a planet the size of Jupiter or Saturn, it's real easy to have things that are a tenth the size of the moon have a very stable orbit around those things. But I thought this would just be a different change of pace, just something that came to mind. And how come nobody else is thinking about these things? Well, once I post the YouTube video for the public, maybe somebody else will figure it out. And the other thing is, if you've got probes that you want to last a long time that far out, and you want a long time to mean like decades, then your power source would preferably be radioisotope thermoelectric generators. And your electricity is from that. But what are you going to use for fuel? Well, you're going to have an ion engine, but an ion engine requires a tank of gas, compressed gas, xenon, krypton, those kinds of things. That's a fixed size fuel tank. You're going to have to come up with some new technology where you have a power source and you have an unlimited fuel supply. And now your probe, your outpost, can be out there for decades. And the only reason you need to replace it is if something fails, or if you want to put out something more capable, something more advanced to replace it. Okay, I knew it was going to be a short one. Any comments or questions before I stop recording?
It's good for thought. Yeah, I like that.
Yeah.
I enjoyed it very much. Thank you.
You're welcome.